Hi, everybody. It's Mr. Molikash again. This is our second in a series of videos talking about compositions of functions. We're wanting today to find the values of what are called composite functions. So instead of composing functions of a sum or difference or product or quotient, we're going to compose a function from another function. So a function is going to be built on another function. So that's sort of a novel idea. And we're going to be finding values of these things that we call composite functions using algebraic, graphical, and tabular representations. So in the last video, we were just looking at the algebraic part of the functions, doing basically manipulation of numbers and symbols, algebraic methods, right? So today we're going to be looking at graphs and tables of ways of looking at functions as well. Okay. So what is a composite function? Before I get started too, I should tell you what the properly named objective from the Math 4 curriculum is. And so this is what we were talking about in the last video, but in this one, we're going to execute a procedure to determine the value of a composite function at a given value when the functions are in algebraic, graphical, or tabular representations, okay? So mine was a little simplified from that, but there's this idea of a given value. So you'll see what that means as we keep on moving. And then you'll see here that this is a composite function as opposed to composing two functions. So these are slightly different things and similar sounding ideas, but they're not the same, right? All right, so so we'll stop presenting that slide. Okay, so to illustrate this, a composite function. So let's talk about what is a composite function. All right. Remember how in the first video I started talking in a little bit of weird language. I would say f is composed of x, and f composed of x is 2x plus 5. So x is sort of the building block of this function. And then there's this other function called g. G is composed of x, and it's x minus 1. So what a composite function is, and I'm going to write this down. It's going to seem confusing. Okay, but the idea of a composite function is when the range of one function becomes the domain for another function. Yep, I know that doesn't make any sense right now, but that's okay. All right. So the idea is that we find some x and y values for a function. We can pick either f or g, and we have a table. We'll start with a table of values, okay? So a table of values, we'll say that f of x has the following table of values. So x, f of x. All right. So we'll put some numbers in, just 1, 2, and 3. Okay. When x is 1, we can put 1 in the place of x and do 2 times 1 and then add 5 and we get 7. Same thing with 2. We can input 2 into the place of x. 2 times 2 is 4. 4 plus 5 is 9. If we put 3 in, we get 11. Okay. So obviously, the domain values from this table of values, the set of values in the domain are 1, 2, and 3. The set of values in the range are 7, 9, and 11. So what a composite function would do is take this set of numbers and make them the new x's for the g function. So I'm not going to write down x and g of x just yet, and I'll explain why in a moment. But let's say that 7, 9, and 11 are now domain values for G. So these were range values for f, range values of the one function, but these are now going to be moved to the domain of another function. All right, so these are sort of chained together. Like G can't figure out what its values are until it first gets some information from f. And it's kind of like the game of telephone, right? You can't pass on information to the next person until you've gotten it from the previous person, kind of thing. So that's kind of what's going on. All right, so let's put 7 in the place of x here. 7 minus 1 is 6. Sorry about the little hook for the G there. 9 minus 1 is 8. 11 minus 1 is 10. All right, now there's a reason why I left the x's out here, because they're not really x's, right? These numbers were f of x's. These numbers came from f, right? So if I get to copy these numbers, I'm going to copy the label down as well. And those are the things that I put inside the function. So this is actually called g of f of x. G of f of x. And this is what the notation looks like for a composite function. You would say g of f of x. Now, can we do f of g of x? Yes, we sure can. We can do that. So we'll see if that makes sense. We can do that too. We can look at g composed of x, where x is the input, right? And then we can let f be composed of g. Okay, so you'll have to kind of remember, I've made my camera really big here. My fingers look huge in this video, but you get the idea, right? If I put 1, 2, and 3 into the g function, I just have to subtract 1 from all my x's. So let's see, I get 0, 1, and 2. So those numbers come over here now, and those numbers are going to go into my f function. All right, now I know that you're probably feeling confused right now. Give yourself some grace, breathe, it's okay. You can always rewind and play this again and again and again. But keep in mind, I took this set of numbers that was a range and now is becoming a domain, okay? So what am I going to do with my 0, 1, and 2? I'm going to put them into my f function, right? So if I put 0 in the place of x, I get 2 times 0 plus 5, which is 5. Maybe you can see me write that at the bottom of the screen there. Maybe I can fit it in there still. Okay. If I put 1 in, I get 2 times 1 plus 5, which is 7, and 2 times 2 plus 5 is 9. All right. Okay, so you can see that f is composed of g of x now. F is not composed of x anymore. This is what happens when f is composed of x. But this is what happens when f is composed of some different set of domain values, namely the range from g. Okay, so we say in this sense that f is composed of g of x. Here we would say f is composed of x. So this language, this kind of thing, tends to be confusing to students to start with, but it gets easier. It gets easier. Okay, so this is what happens when we look at compositions of functions from a table of values. We're going to do this from a graphical perspective now. So I'm going to switch screens and go graph the f and g functions, whoops, in Desmos. And okay, here we are in Desmos. So I'm going to start labeling things. F of x is 2x plus 5. In Desmos, by the way, I would try, if I were a Math 4 student, I would open a new tab while I'm doing this, pause the video, and type it in just like Mr. Molakash is doing. G of x equals, this is some good practice at just using the good old Desmos calculator. All right, you can see that both of these functions in and of themselves are linear functions. The first function is a slope of 2 and a y-intercept of 5. I guess I can make this a little better looking. Okay. And what happens is I can take values from f. Okay. So I can create a function, and I can say, hey, Desmos, graph the composition of f and g. So the first one we did, I know you can't see this, but I'm pointing at g of f of x. So you can have Desmos graph g of f of x. Okay, and if I want to find g of f of x, okay, where x is 1, the answer should be 6. Let me kind of stop this for a moment and say that again. So if I want to find g of f of x evaluated when x is 1, when g of f of x is evaluated when x is 1, the answer should be 6. When this function is evaluated at x equals 2, the answer should be 8. When this function is evaluated at x equals 3, the answer is 10. Now, I want you to see, let me go back to the Desmos calculator, and I want you to see what happens there. Okay, so if I slide this graph around, if I find out what happens at x equals 1, sure enough, I get 6, if I can get my, right? So when x is 1, that makes gf a certain number, right? Namely 7. And then if I put the 7 here, I get 6, right? So the 0.16 is on this new composition function, this function that's composed of f of x. Namely, 2,8 is also on the graph, and 310 is also on the graph. Right, so I want to kind of illustrate that the graph of this composed function g of f of x is telling us the final values when x, the original x's, if you will, are 1, 2, and 3. Okay, so there's kind of a chain reaction. There's this middleman step. You have to kind of go through the middleman to get to the final answer. So this wonderful thing called Desmos kind of cuts out the middleman and does the composition for you, and you can see the function values right there. Okay, if I wanted to do the same thing with, sorry, I've covered this up, f of g of x, and you were taking some good notes, then you remember that when x is 1, 2, and 3, the final values were 5, 7, and 9. And so I can kind of, when x is 1, the final value is 5. When x is 2, the final value is 7. When x is 3, the final value is 9. And sure enough, that is the values that we can get. So if we are given a value, given a 1, 2, and 3, we ought to be able to find the values of this composition, the final composition values, 5, 7, and 9. Okay, so yeah, that's kind of what we were reading before, like given a value. What they're giving you is 1, 2, and 3, and they're asking you to jump through some hoops to find the final answers, 5, 7, and 9. So this is a graphical way at looking at the same information that we got before, right? So when x is 1, we get a final value of 6 for this g composed of f. When x is 2, g composed of f is 8. When x is 3, g composed of f is 10. When x is 1, f composed of g is 5, and so on and so on. You can also see that these are different things, like the outcome is different. So these two things are, the order in which you compose the two functions matters, because you can get different results. You can get different results. Okay, so we looked at a graphical way of finding this. The last thing we need to do is look at an algebraic way of doing this. And so I'm going to show you on the next page here f of x again was 2x plus 5. G of x is x minus 1. Okay, so if we don't have a table of values, we don't have a graph, what can we do? What can we work on? So what we can do is, for our function g composed of f of x, okay, what I tell people is to take the x out and replace this input, this x, with the entire function, okay? So instead of g of x, I have g of f of x. So instead of x minus 1, I'd have f of x minus 1. Now, keep in mind, f of x is this function here, right? So what I can do is replace f of x with this expression, 2x plus 5, minus 1 now, because the g is telling me to take something and subtract 1, and so I get 2x plus 4. All right, so now I can find values for any input, right? So if x is 1, then I can put 1 straight into this and get 6. Whereas before, when I did this with a tabular way of doing it, right, to get 6, I had to first find f of x. I had to get the 7 for f of x and then put 7 into the g of x function and get 6. But this is sort of the way of finding it straight off without having to do that. It's an algebraic way of doing it. Okay, so this is the composed function itself. The thing that we were graphing just now in Desmos was a new line that was the f of x function, but it was moved a little bit, right? Okay, so when x is 2, 2 times 2 is 4, 4 plus 4 is 8, 2 times 3, 6 plus 4 is 10. And sure enough, those are the same values, 6, 8, and 10, that we got here, 6, 8, and 10. So here, again, we had to first find what f of x was and use that range as the domain for our new function. But if we do this algebraic way of composing functions, we don't need to put numbers into f of x anymore. We can just compose the two functions algebraically and then find the values, okay? All right, same thing can happen for, and I'll do this next one in a different color, blue, I suppose. If we wanted to compose f of g of x, right? So if we look up here, f of x is 2x plus 5. So f of g of x would be 2 times g of x plus 5. So what we're doing is a substitution. We're taking the x's out because f is no longer composed of x. F is composed of g of x. This is the new input of the function, all right? And g of x, of course, we remember is the function x minus 1. So now we can execute an algebraic procedure, right? We can multiply and combine like terms. So we get 2x minus 2 plus 5, which is 2x plus 3. And just to illustrate, our function now is called f composed of g, right? All right, so f composed of g, what happens when x is 1, when x is 2, and when x is 3? Well, when x is 1, we can put x right here, and 2 times 1 plus 3 is 5. And when we put 2 there, we get 7, and when we put 3 there, we get 9. And sure enough, that's what happened when we did this with a table of values, right? When x was 1, f composed of g was 5. When x was 2, f composed of g was 7. When x is 3, f composed of g is 9. So instead of using a table of values or a graph, we can execute this algebraic procedure to find the values of a composite function just by using the given value. All right, so this is tough stuff. This is going to take some practice on your part, but I'm here to help you. Mr. Guthrie is here to help you. Please visit us during office hours, and please, 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 if you didn't do this, go back and watch this again and take some good notes. Write down some questions. Tell us what you need help with, because without your feedback and without your input, our hands are tied and we can't do anything. All we can do is lecture and give you information. But teachers need to make sure that you're learning and you're absorbing this information. So help us teach you and not just lecture. Okay, so I hope you guys have a great day. Again, reach out to me if you need help. See you soon.